Good morning, ITI1100 students. I hope everything is well with you, and today we will resume our lecture towards addressing all the objectives of Module 1. So, in the previous lecture, we addressed the importance of binary systems in digital electronics, as well as we successfully learned how can we represent any number in any numerical system, and how can we convert between numbers in different bases. And today what we will do is understand the how can we proceed with the operation, with the arithmetic operations in the binary number. But why we're doing that? Remember, like when it comes to the binary numbers, they are very important in digital system because as a natural coincidence, most electronic components operates in a binary mode. So the switch can be either open or closed, indicating a 0 state and a 1 state. A transistor can be either not conducting or conducting, indicating again a 0 or a 1 state. So this two-state nature of the electronic component can be easily expressed with the help of binary numbers. Another reason is the computer circuits have to handle only 2 bits instead of 10 digits of the decimal system. So this simplifies the design of the machine as well as reduce the cost and improves the reliability. Okay, so what are the operations that can be done using a binary notation, and how can we proceed with that is the main goal of today's lecture. So those operations are something similar to what we understood in the what we learn in the elementary school, which are addition, subtraction, multiplication, and division. How these operations are performed, that's what we're gonna cover in the next slide. So shall we begin? So when it comes to the binary addition, so the addition follows the same rules as the addition in the decimal systems, except rather than carrying a 1 over the values added equal to 10, the carryover occurs when the result of additions is equal to 2. As you can see, guys, here when I added 0 plus 0, the sum will equal to 0 and there should be no carry. 0 plus 1 is the sum will equal to 1 and there should be no carry. However, on this case, when I add 1 plus 1, that is equal to 2 in decimal, and the 2 in decimal can be represented by 1 and 0. So that is the only difference between binary and decimal when it comes to the addition. So let's take a look on an example here at which we're gonna apply what we learned in the previous slide. So let's suppose I would like to add this operand to this operand. So if I add 1 plus 1, I should start my addition from left to right. So 1 plus 1, the answer should be 0, and I should have a carry of 1 here. And when I add 1 plus 0, the answer should be 1, and there should be no carry, so the carry should be equal to 0. When I add 1 plus 1, the answer should be 2, so it's 0 and a carry of 1. Here I have 1 plus 1 plus 1, so that is an indication of having a 3. So 1 plus 1 plus 1, that is equal to 3. So I have a sum equal to 1 and a carry equal to 1 as well. Okay, now, so I have 1 and 1 here, and this will give me 2. This will give me again 2. Okay, 0 and 1. So if I would like to check my work, so remember, like in order to convert this notation to decimal, I should use the polynomial notation, at which I will go and multiply this one by 2 to the power 0, this 0 with 2 to the power 1, and this one to 2 to the power 2, and so on. So if I did so, as you can see, like converting this sum here, which is basically, as you can see, this is 64, this one is 2 to the power 6, which will give me 64, and this will give me 8, and this will give me 2, so 2 plus 8 equal to 10 with 64, 74. Okay, now 45 plus 29 is apparently 74 in decimal, which is equal to 1001010 in binary. Okay, now what about an example at which we're adding a plus b plus c? So how can we do that? So the answer is so easy. So we should add a plus b, then add it back to c. So if I'm gonna add 0 plus 0 plus 0, the answer should be 0. 0 plus 0 plus 1, the answer should be 1. 0 plus 1 plus 0, the answer should be, the sum should be 1. And here this will give me 0 and a carry of 1 because this is apparently 2. And this is again 0 and 1. And here it's gonna be 1 and a carry over of 1. And this case here is an interesting case because I'm adding 4 ones at the same time. So the answer should be, according to this, is 100. So that's why I added 100 here. Okay? Okay. When it comes to the subtraction, so similar to the addition, there is a little difference between binary and decimal subtraction, except those that arise from using only the digits 0 and 1. So basically, if you're subtracting 0 minus 0, the answer should be 0. 1 minus 1, the answer should be 0. 1 minus 0, the answer should be 1, because 1 is greater than 0, so it's going to be like 1. But however, here, that is the interesting and the tricky part. The only case where the borrowing is necessarily when 1 is subtracted from 0. When this occurs, the 0 in the borrowing column essentially becomes 2, changing the 0 minus 1 to be equal to, that is equal to 2 minus 1, which is equal to 1. So in other words, this 0 has to be like borrowed from somewhere, from the left side, and this will become 1 and 0 minus 1, and this will become 1, and a borrow here should happen. Okay, so to apply that, let's take a look on this example. Like if I would like to subtract 10111 from 100, which I will subtract 1 minus 1, and this will give me 0. And here I have to subtract 0 minus 1. But since it doesn't go, what I have to do is to borrow from this one. This one apparently will become 0, and this one will become 1 and 0. 1 and 0 will give me 1. And here, unfortunately, here I'm subtracting 1 from 0 again, so I have to borrow from here. When I borrow from here, this will become 0, and again this one will become 1 and 0. So 1 and 0 minus 1, this is 1. Fortunately, this 0 has to be subtracted from this 0, so it's a straight 0. And here 0, I have to 1, I have to subtract it from 0, so I have to borrow from this 0, but I cannot borrow, so I have to borrow from this one. So this one will become 1, and this one will become 1 and 0. So 1 and 0 minus 1 will give me 1, and 1 minus nothing will give me 1. Okay? Okay, when it comes to multiplication, what you have to do is to apply what you learned at the addition and to repeat the addition multiple times. So if you remember, guys, if I would like to multiply 11 by 12, so what I will do is multiply this to 2020, and then I have to shift, and this has to become 1 and 1, and this is 2, and this is a 3, and this is 1. So I have to apply the same principle here. So let's take a look at this example at which I am multiplying 4 to 3. So what we'll do is I will start with the first digits, which happen to be 1. So when I multiply 1 by 100, the answer should be 100. I will move to the next digit, which is 1 again here, and multiply it by 100, which will give me again 100, but I have to shift it to the left. Okay, the last digit here, the last digit is equal to 0, so it doesn't matter if I multiply it or not. And since I have no more digit to multiply, what I have to do is to do a direct addition. So what will happen is we'll put a 0 here, so 0 plus 0, 0, 0, 1, and 1. That is equal to, guys, this is 8 plus 4, and this is 12. So 4 multiplied by 3 in decimal is equal to 12. The pencil and paper division, also known as long division, is the hardest of the 4 arithmetic algorithms we learned in the elementary school. So at most basic, long division is 4 process that is repeated for each digit in the dividing. So basically, as you remember, guys, this is from elementary school. So we try to divide 27 with 8. That doesn't go, so I have to put 0 here, and then 84 can be 27 can be divided from 84. So what I have to do now is to see how many times, how to do the multiplication after that. So this is apparently I have to multiply it by 3, and then to do the subtraction. And after I do the subtraction, this will give me 4 minus 1, 3, and then I have to take down the next digit and keep repeating the same process. The good news is binary division is a lot easier than the decimal division. So instead of having to guess how many times our divisor fits into the working dividend, which can get complicated if the number involved are large, in binary division, the answer will be either 0 or 1. Okay? Does it go or it doesn't go? So let's take a look on this example here, guys. Let's suppose I have 1, 1, 0, 0, and I would like to have 3. Okay? So basically this is 12, and we know that the answer should be 4. So 1 doesn't go, so I have to add 0, and after that 1, 1, yes, it goes, so I have to add 1. So multiply it 1 and 1. So what will happen is after that I have to do the subtraction. So this will give me 0. I have to bring down this 0, and it doesn't go, so I have to add 0 and bring back the second 0. It doesn't go, so I have to put 0 here, and apparently the answer here is equal to 4, and the remainder is equal to 0. Let's take a look on a more complicated example. So imagine we have 1011.11 and would like to divide it by 1, 1. The first thing we have to ask ourselves, we have to check whether our divisor has a radix point or not. In this example, it has not. So that's a good news. So first we have to ask ourselves, does 1, 1 goes with 1? No, because it's greater than 1. Does 1, 1 go into 1, 0? No, because it's greater than 1, 0. Sorry for that. Does 1, 1 go into 1, 0, 1? Yes, because it's less than or equal to 1, 0, 1. So what we have to do is to divide 1, 0, 1 by 1, 1. So what will be the answer? There is no guessing here. The answer should be 1, and it's we multiply 1 by 1, 1, and we make the subtraction. So subtract 101 minus 1, 1. the answer will give you 1 0, and then you bring down the next one, making it 1 0 1 again. Then we will do the same step until we reach to the point where it will be equal to 1 0 0. So 1 0 0 is greater than 1 1. Then after that, what we will do is we'll do the subtraction. The answer will be 1. We bring more zeros. What I have to do here, apparently I can't do the division anymore, so I have to stop. Okay, now we're gonna address a new topic, which is complement in any numbering systems. Why we're addressing this topic? Because this principle will make the subtraction much easier. Okay, if you ask yourself a question, if I would like to do a subtraction like this, 9 minus 3, why 9 minus 3 is equal to 6? Okay, so we can do it because we're human and we can understand that we're taking 3 units from 9, and that's why the answer is 6. But when it comes to the computer doesn't understand the minus digit, and that's what we're going to cover in the next slide. So what will happen is we have to complement the 3 to complement a number. So the 3 here belongs to the decimal base. The decimal base means that I have to make, like, to get the complement, it's 10 minus 3. The answer should be equal to 7. Okay, so then what I have to do is to add 10 plus 7, addition, like, basic addition. So 10 plus 7 is equal to 16. Okay, and then I will discard the carry, and as you can see, 6 is equal to 6. And this is how computers are performing the subtraction method. So complements are used in digital computer to simplify the subtraction operation and for logical manipulation. So the simplifying operation leads us to a simpler, less expensive circuits to implement the operation. So basically, as you can see, guys, if you already designed a circuit that will do the addition, you don't need to design another circuit to do the subtraction, because basically you can apply this same principle to do the subtraction and the addition at the same time. So, and actually there are two types of the complements. Okay, the first type is called the radix complement or the R's complement, and if we apply it, okay, if we apply it to the decimal numbering, it's gonna be called the tens complement, because the base in the decimal is 10th, so it's called the tens complement in decimal. And in binary, remember, what's the base in binary is equal to 2, so it's the 2's complement in binary. And the other type is called the diminished radix complement or the R-1 complement. So when it comes to the decimal numbering system, the diminished radix complement is referred to as the 9th complement, because 10 minus 1 is equal to 9. So the 9th complement at the decimal. And for binary, for sure it's going to be the 1's complement, because 2 minus 1 is equal to 1, and it's the 1's complement. But why we need that?
Knowing that how to calculate the complements will save a lot of time as well as cost, because the same circuit used to perform the arithmetic addition can be used to do the arithmetic subtraction with zero extra cost.
Now, how to calculate the radix complement. It's very easy. So basically, if I would like to calculate the 2's complement of any binary notation, I will look on how many bits this binary notation contain. So I have 1, 2, 3, 4, 5, and 6. So 2 to the power 6 minus this, by doing this subtraction, I will be able to get what? I will be able to get the 2's complement of any notation. And when it comes to the 10th complement, it's the same thing. So the 10th complement, how many digits in the 10th? 1, 2, 3, 4, 5. Remember 5, so I have to weight the base to 5. So 10 to the power minus 5 minus this number will give me the 10th complement. Okay. However, when it comes to binary, there is a shortcut method that I'm going to share it with you. So basically, you don't need to do the subtraction. What you have to do is you have to look to your number from left to right. And once you examine the first one, you keep it. You copy all the numbers. And once you get to the first number here, you keep it. And you flip all the others. So the 0 will become 1. The 1 will become 0. The 0 will become 1. And the 1 will become 0. Okay, let's take another example here. So we examine all the bits from left to right. Fortunately, the first one is here. So I will copy it and then I will flip all the others. So the 0 will become 1, 0 will become 1, 1 will become 0, the 0 will become 1, and 1 will become 0. Okay? For the diminished radix complement, what you can do is to calculate the radix complement and subtract it by 1 at the end. Or what you can do is look how many digits here. We have 1, 2, 3, 4, 5, 6. And remember, 6, we have 10 to the power 6 minus 1. This will give me 9, 9, 9, 9, 9, 9. And what I have to do is to subtract this number from it. So this will give me the 10th complement. When it comes to the 1's complement, it's still the same. So I have 1, 2, 3, 4, 5, 6, 7. So 2 to the power. So here it's going to be that represent 2 to the power 7 minus 1. Okay. Minus the number that I would like to get the 1's complement of it. And this will give me the 1's complement. Okay.
There is a shortcut as well to calculate the 1's complement. From the destination number, what you can do is to start flipping the bits one by one. The 1 will become 0 and the 0 will become 1. And that's it. You can do the same for the another example. And this is the most powerful and effective technique.
Okay. A positive integer, including 0, can be represented as unsigned number. However, to represent negative integer, we need a notation for negative values. Like in general, like in ordinary arithmetic, a negative number is indicating by having a minus. Like if I want to say that I have minus 3, it's very easy to do so. If I have minus 4, just by putting the minus notation to indicate that this number is negative. Okay. However, computer cannot understand a minus state. So because of hardware limitation, computer must represent everything with just binary digits. So how to overcome this problem is to do to follow a customary approach at which the sign with a bit placed at the leftmost position will represent the sign. Now, we have to follow 3 different approaches to represent the signed binary numbers. The first approach is the signed magnitude, and this approach is easy for a human, but it's very hard to be deployed to computers. Okay, so let's suppose that I have number 3, and I would like to represent it using 8-bit representation. Remember, like guys, when it comes to represent the binary, you have to know how many bits you need to represent the number. And apparently for 3 we only need 2 digits. Okay, so it should be just 1 1. But for the signed magnitude to work, we have to agree in the specification of how many bits should we use to represent that number. So we will toggle just the leftmost bit. Okay, so in any questions that I'm gonna give you in the specification, I will say like like number 15, show me the minus 15 using 15. You need 4-bit to represent 15 because it's less than 2 to the power 4, which is equal to 16. Okay, but still, I have to give you how many bit you should use to represent that number. So here it clearly says it's using 8-bit representation, because at the end of the day, and this is what we're gonna tackle in the last chapter, in order to represent any bit using digital component, we need to use a flip-flop. The flip-flop will store just 1 bit. So we need to know how many flip-flop we need to use in order to represent any notation. Okay, so using the 8-bit here, if I would like to indicate that 3 is in a negative magnitude, what I have to do is to make sure that the leftmost bit, or the most significant bit here, is what is equal to 1. Okay, as you can see, this is the magnitude and this is the sign bit. Okay, this approach is not recommended when it comes to to digital
electronics, the most widely used is the ones and the twos complement representation.
using 8 bits. So I know the magnitude of 3 is 100. Then I have to add 5 zeros at the beginning. Okay, and the last one should be equal to 0. That is representing what? Plus 3. Okay, that's equal to plus 3. Now the plus 3, I should convert it using the ones complement to what? Complement shortcut to get minus 3. Okay, so basically to do so, what I have to do is to flip all the bits when it comes to this. So what I have to do, this is 0 0, and all the others are 1s. Okay, and still, as you can see, the leftmost bit is equal to 1, which goes with the principle of having the leftmost bit equal to 1 to indicate minus 3. For the signs 2's complement representation, it's still the same. Again, we go and represent our number in the positive. So like again, we have 1 1, and then we have 6 zeros at the beginning, 0 0 and 0 0 and 0 0. What you have to do in order, you remember, like that's equal to plus 3. To get the minus 3 in the 2's representation, you keep this one and you flip all the others. So this will become 0, this will become 1 1 1 1 1 1, and look at this, it's still equal to 1, which indicate that is equal to minus 3. Okay, so the following table depicts all the possible 4-bit signed binary number in the 3 representation, using the sign magnitude here, using the signed ones complement, and using the signs 2's complement. Okay, as you noticed, the most prominent one is the sine 2's complement, because as you can see, the sine 2's complement has only, like you can see, has only a positive 0. Okay, that's it. There is no negative 0, and when it comes to the sine 2's complement. However, using the sign magnitude of the sign magnitude notation will induce a negative 0, which is not correct, as well as the sine 1's complement will induce as well a negative 0, which is not correct. Okay, so on all my questions we should use the sine 2's complement to represent a negative number. Okay, so some might ask, okay, why do we need to go over the hassle of learning how to represent a number in negative? The answer is so straightforward. The direct method of subtraction taught in elementary schools, that is, uses the borrow concept, at which you are borrowing a 1 from a high significant position when the minor digit is smaller than the superhanded digit, can work effectively when it comes to human doing and performing subtraction with paper and pencil. However, when it comes to the digital hardware, this method of borrowing doesn't work, and it's not efficient, and will induce more component to be deployed. Like imagine that you already built an adder and you need now to order the same component just to do a subtractor. This can be easily tackled and solved by converting the subtraction into an addition. So remember, guys, when it comes to a minus b, this can be written, when it comes to the 2's complement, I'm talking, as a plus minus b. And minus b can be done by getting the 2's complement of b. And when it comes to the 1's complement, a minus b is equal to a plus minus b plus 1. Okay, where minus b here indicates the 1's complement. Okay, so let's take a look on an example here. Okay, guys, now let's suppose that I asked you, and this question might come in the midterm, that I ask you to show me in details how to convert a number from decimal to binary, and then how to perform a minus b using the 2's complement method. So basically, remember, like, plus a is equal to 84, and in order to convert 84 to binary, we use the method covered in a previous lecture, the strip of method. So basically we divide 84 over 2, and the answer is 42, and the remainder is 0. And then again, like 42 divided by 2, the answer is 21, and the remainder is 0. And then like 21 divided by 2, the answer is 10, and the remainder is 1. And 10 divided by 2, the answer is equal to 5, and the remainder is 0. And again, 5 divided by 2, the answer is 2, and the remainder is 1. 2 divided by 2, the answer is 1, and the remainder is 0. And 1 divided by 2, the answer is 0, and the remainder is 1. And if we go from bottom to top like this, the 84 in binary should be equal to 1010100, as you can see here. So if you do the same concept, you can get B, okay? And this will indicate positive B, okay? So basically what we have to do is, that represent the positive A, and this represent the positive B, okay? And I would like to calculate A minus B. So minus B here is basically the 2's complement of whatever I got here, okay? So, and remember here we are doing it using the unsigned notation, okay? Because when I do the when I do the complement, what I have to do is to keep this one and flip all of them, okay, the addition. And after I do the addition, if I get 1, I have to ignore it because the result is positive. That will tell me that the result is positive. Why I know that? Because apparently A is greater than B. If I get no carry, then B is larger than A and the result is in negative. So I have to take the 2's complement.
As a homework, please do an exercise at which you should calculate B minus A.
Okay. Okay. Doing the subtraction using the 1's complement is much easier, so as explained, you have to get the binary representation of A, the binary representation of B, and to get the minus B, you have to do it using 1's complement of B will be equal to 0, 0. We flip 0, 0, and this is 1, 1, 1, 1, and 0, okay? So basically, we copy A as is, and for B, this will be like, again, this is 0, we flip it 0, and we flip all those zeros to 1, 1, 1, 1, 1, 1, and this 0. And
After that, we do a direct addition between A and the 1's complement of B. Then we add the carry at the end.
of fact, let me give you this example. So if I would like to do the subtraction in decimal, 9 minus 4, okay, using the 9th complement, okay? So what is the 9th complement of 4? Okay, so the 9th complement of 4 is 5. So 9 plus 5 is equal to 14. Okay, so what I have to do is I have to add the carry here. So 4 plus 1 will equal to 5. So 9 minus 4 is equal to 5. And I did it using the diminished radix complement, which is the 9th complement. Okay, I would like to explain what's called BCD. So as you noticed, computers only understand binary, but sometimes we want the human to get the output in a notation that can be understood by the people from different domain. We should not stick the output to just people from the electrical engineering and the computer science domain. As such, we can trick the computers to understand binary coded in a decimal. To do so, what we have to do is to represent each number from the decimal symbol into the equivalent binary symbol. However, each digit in the decimal should be represented
in 4 bits, and the
10th. As you can see here, we have the digits from 0 to 9, and that's something similar to to the binary. When it comes to the 10th, no, for the 10th, to represent the 10, we should do something similar to the decimal. So we have to convert 1 was equal to 0, 0, 1, and we have to convert the 0 using the 4-bit, so 0. That is MBCD, okay? So using this technique, we can instruct the computer to produce the output in a way that is similar to the decimal. And if we have like the 7-segment display that we're gonna introduce later, apparently like another people can easily understand that this is 10, okay?